Gases dissolve in liquids to form solutions. Generally, gases that are easily liquefiable are more soluble in a solvent. For example, carbon dioxide is more soluble in water than oxygen at a given temperature. Oxygen dissolves in water to a very small extent, about 5 to 10 milliliters per liter of water. However, even this small quantity can sustain aquatic life. The dissolution of gases in liquids is an equilibrium process. At equilibrium, the rate at which the gaseous solute molecules escape the solution equals the rate at which the molecules re-enter the solution. An increase in pressure results in more molecules of the gas striking the surface of the liquid and entering the solution in a given time. Therefore, at high pressure, more gas dissolves in a given volume of liquid than at lower pressures. This proportionality of the solubility of a gas to pressure was first proposed in 1800 by William Henry and is known as Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas. Dalton, a contemporary of Henry during the same period, concluded independently that the solubility of a gas is a function of its partial pressure. If the solubility of a gas is expressed in terms of the mole fraction, then the statement of Henry's law becomes: the mole fraction of a gas in a solution is proportional to the partial pressure of the gas over the solution. However, the most commonly used version of Henry's law is: the partial pressure of a gas in vapor phase, P, is proportional to the mole fraction of the gas, X, in a solution. Mathematically, it can be represented as P is proportional to X, or P is equal to KHX, where KH is the Henry's law constant. Further, if you plot a graph between P, the partial pressure of a gas in vapor phase, and X, the mole fraction of the gas in a solution, then you will get a straight line passing through the origin with its slope equal to KH. The graph also shows that as P increases, X, the mole fraction of the gas in a solution, also increases. The Henry's law constant, KH, for some common gases in water as the solvent are given in the table here. On comparing the values of Henry's constant for oxygen and nitrogen, we can infer that the value of KH increases with an increase in temperature. As a consequence, the solubility of gases generally decreases with an increase in temperature. Also, if the dissolution of gases in liquids is considered as a process similar to condensation, then it is an exothermic process, where a dynamic equilibrium is established between the gas and the solution phase. On applying Le Chatelier's principle to this equilibrium, we see that the solubility of a gas decreases with an increase in temperature. It is seen that when water is heated, bubbles of gas appear on the sides of the container well below its boiling point. These are bubbles of air, which are evolved when water, which is air saturated at lower temperatures, is heated. It is interesting to note that hot water tastes flat because the oxygen in it has been expelled by heating. Have you ever wondered why aquatic species are more comfortable in cold water rather than in warm water? This is because the solubility of oxygen is more at low temperatures. Let us now discuss some important applications of Henry's law in the industry as well as in biological solutions. Carbonated drinks are packed under high pressure of carbon dioxide, some of which gets dissolved in the beverage. When the bottle is opened, the partial pressure of carbon dioxide above the solution drops. As a result, some of the dissolved carbon dioxide comes out of the solution as bubbles. Henry's law has an important application for scuba divers. The pressure is very high deep in the sea. As a result, the amount of nitrogen dissolved in the blood and other tissues of deep-sea divers increases. If the diver returns to the surface too rapidly, then the nitrogen forms bubbles in the blood as it becomes less soluble due to a decrease in the pressure. These bubbles are dangerous as they can plug small arteries and cause serious damage by stopping the flow of blood to a particular organ. Divers may experience this potentially painful and lethal condition called the bends if they do not ascend to the surface slowly, allowing themselves time to adjust to the lower pressure at the surface. To alleviate this problem, artificial breathing mixtures consisting of 32.1% oxygen, 56.2% nitrogen, and 11.7% helium are used. Helium is 5 times less soluble in blood than nitrogen. As a result, there is less dissolved gas to form bubbles. On the other hand, at high altitudes, the atmospheric pressure is low and there will be less concentration of dissolved oxygen in blood and tissues. Therefore, mountaineers at very high altitudes suffer from anoxia, which is low oxygen supply in the tissues, accompanied by weakness and inability to think clearly. That is why mountaineers carry oxygen cylinders at high altitudes. Let us now discuss the vapor pressure of binary solutions. We shall discuss the vapor pressure of liquids in liquids and solids in liquids. First, we will discuss a binary solution of 2 volatile liquids, 1 and 2, that are completely miscible in all proportions. In 1886, through experimental studies, a French chemist M. Raoult established a quantitative relationship between the mole fraction of a given component and the partial pressure exerted by it The law states that the partial vapor pressure of each component in the solution is directly proportional to the mole fraction of it in the solution. Now, if P1 and P2 are the partial pressures exerted by the components 1 and 2 at a certain temperature, then, according to Raoult's law, P1 is proportional to x1, or P1 is equal to P1 naught x1, where P1 naught is the constant of proportionality and represents the vapor pressure of pure component 1 at the same temperature. Similarly, for the component 2, P2 is equal to P2 naught x2, where P2 naught represents the vapor pressure of the pure component 2. Now, if you apply the Dalton's law of partial pressure, the total vapor pressure of the mixture would be equal to the sum of the individual partial pressures of the component 1 and 2. That is, P total is equal to P1 plus P2, or P total is equal to x1 P1 naught plus x2 P2 naught. Let this be equation number 1. Further, you know that for a binary solution, the sum of mole fractions x1 and x2 is equal to 1. Or, we can write x1 equal to 1 minus x2. Now, substituting for x1 in the equation 1, we get P total is equal to 1 minus x2 P1 naught plus x2 P2 naught. Let this be the equation 2. In the equation thus obtained, we can see that P total is a linear function of mole fraction x2 as P1 naught and P2 naught are constant at a particular temperature. If a graph is plotted for the partial vapor pressure of the first component against the mole fraction, corresponding to the equation P1 is equal to x1 P1 naught, then a plot as shown here is obtained. As you can see in the graph, when the mole fraction of first component becomes 1, the partial pressure of component 1 is the vapor pressure of the pure component 1. Similarly, a plot for the component 2 corresponding to the equation P2 equal to x2 P2 naught on the same set of axes is represented as shown here. Now, as can be seen from the curve, the vapor pressure of the pure component 2 is higher than that of the pure component 1. This means that the component 2 is more volatile than component 1. Now the total vapor pressure of the binary mixture P total is given by the sum of the partial pressures P1 and P2. As you can see in the diagram, the solid straight line gives the plot of P total versus mole fraction. Further, as the vapor phase is in equilibrium with the solution phase, the composition in the vapor phase can be determined by the partial pressures of the components by the equation P1 is equal to Y1 P total and P2 is equal to Y2 P total, where Y1 and Y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase. It is important to note that the above holds true only if the two components in the binary solution are volatile and are completely miscible with each other. Now, if one of the components in the binary solutions is considered to be highly volatile, such that it exists as a gas, then, as you know, its solubility is given by the Henry's law, P is equal to kHx. As can be seen from the equation, the partial pressure P of the highly volatile component or gas is directly proportional to the mole fraction X, and Kh is the constant of proportionality which can be equated to P0. In other words, we can say that Raoult's law is a special case of Henry's law. Let us now discuss the vapor pressure of binary solutions of solids in liquids. That is, Raoult's law for non-volatile solutes. A non-volatile solute has no tendency to form vapor at the temperature of the solution, and it will therefore not contribute to the total vapor pressure of the solution. For example, in a solution of salt in water, salt is a non-volatile solute and does not contribute to the total vapor pressure of the solution. Thus, the vapor pressure of the solution will be the vapor pressure due to the solvent only. That is, P total is equal to P1 or P total is equal to X1 P1 naught, where P1 naught is the vapor pressure of the pure solvent at a particular temperature and X1 is the mole fraction of the solvent 1. On the basis of Raoult's law, the liquid solutions can be classified into ideal and non-ideal solutions. Let us first discuss the ideal solutions. A solution that obeys Raoult's law over the entire range of concentration is said to be an ideal solution. For an ideal solution, the enthalpy of mixing and the volume of mixing of the pure components are zero. This implies that no heat is evolved or absorbed, and also there is no change in volume on mixing of the two components. For example, if 50 ml of hexane is mixed with 50 ml of heptane, the volume of the solution obtained is exactly 100 ml, and no heat is evolved or absorbed in the process. At the molecular level, the ideal behavior can be explained in terms of the intermolecular attractive interactions between the two components. If A and B are two components, then in an ideal solution, the magnitude of A-B interactions will be same as the magnitude of AA and BB interactions. However, in real life, there is actually no such thing as an ideal mixture, but some liquid mixtures get fairly close to being ideal. These are mixtures of two very closely similar substances. Some common examples of mixtures that show nearly ideal behavior are hexane and heptane, benzene and methylbenzene, chloroethane and bromoethane. Since ideal solutions obey Raoult's law, they show the graphical behavior as shown here. Let us now discuss non-ideal solutions. Solutions that do not obey Raoult's law over the entire range of concentration are said to be non-ideal solutions. Non-ideal mixtures produce curves rather than straight lines as shown here. The dotted straight lines represent the ideal behavior and the curved lines represent the deviations from the ideal behavior. The reasons for the deviation are the intermolecular interactions at the molecular level. For a non-ideal solution, the magnitude of AB interactions is not same as the magnitude of AA and BB interactions. Also, delta H mixing is not equal to 0 and delta V mixing is not equal to 0 for such solutions. If the magnitude of AB interactions is weaker than the magnitude of AA or BB interactions, then this implies that such solutions have a higher tendency to escape in the vapor phase and will show a higher vapor pressure. Such solutions are said to exhibit positive deviation from Raoult's law. The total vapor pressure of such a solution is greater than the vapor pressure corresponding to the ideal solution of the same composition. For example, a mixture of ethanol and cyclohexane shows positive deviations from the Raoult's law. Ethanol exists in highly associated form due to hydrogen bonding. On addition of cyclohexane, its molecules get in between and there is a considerable reduction in ethanol-ethanol hydrogen bonding. As a result, it becomes easier for the ethanol molecules to escape into the vapor phase, and thus we see the positive deviations from the Raoult's law. For a positive deviation, delta H mixing is greater than 0 and delta V mixing is also greater than 0. Methyl alcohol and water, carbon tetrachloride and chloroform are some other solutions that exhibit positive deviation from the Raoult's law. On the other hand, if the magnitude of AB interactions is greater than the magnitude of AA or BB interactions, the escaping tendency of A and B type of molecules decreases and the partial vapor pressure of each component decreases. This in turn results in the decrease of the total vapor pressure of the solution. Such type of solutions are said to show negative deviations from the Raoult's law. As you can see here, formation of a H bond takes place between the chloroform and the acetone molecule. This decreases the escaping tendency of the individual molecules and results in negative deviation from Raoult's law. For the solutions exhibiting negative deviations, delta H mixing and delta V mixing both are negative. A few more examples of non-ideal solutions exhibiting negative deviations are phenol-aniline and chloroform diethyl ether solutions. A detailed look at the two graphs show that there are some large deviations from ideal behavior at specific compositions. These very large deviations from ideality form a special class of mixtures known as azeotropes or constant boiling mixtures. Azeotrope is thus defined as a special class of liquid mixtures that boil at a constant temperature and at a certain composition. At this condition, the mixture behaves as if it was a single component with one constant boiling point. In such cases, it is not possible to separate the individual components of the mixture by fractional distillation. Azeotropic mixtures can be further classified into two categories: minimum boiling mixture and maximum boiling mixture. Let us first discuss the minimum boiling azeotrope mixtures. When the positive deviations from ideality are sufficiently large, the mixture is said to be a minimum boiling azeotrope. As you can see from the graph, the total vapor pressure of the azeotrope is given by the maximum, represented as O in the curve. Now, as the vapor pressure is maximum at this point It gives a minimum boiling azeotropic mixture. At this point, O, the concentration of the vapor phase is the same as the concentration in the liquid phase and is referred to as the azeotropic concentration. Ethanol and water form a minimum boiling azeotrope at 351.15 Kelvin and at a composition of 95.4% ethanol and 4.6% water. Let us now discuss the other type of azeotropic mixtures, the maximum boiling azeotropic mixtures. When the magnitude of negative deviations from ideality is very large, the total pressure curve in such cases passes through a minimum X. As you can see in the diagram, the point X corresponds to the minimum vapor pressure, so this will result in a maximum boiling azeotropic fraction. Nitric acid and water is an example of maximum boiling azeotrope. The azeotropic composition of this mixture at 393.5 Kelvin is 68% HNO3 and 32% water.